So in the last few minutes, we looked at ways to speed up the jumping even faster than this. Okay, this doesn't speed it up, it just makes it correct. But we're always looking for opportunities to make the performance faster. And obviously at this point, we're improving the hardware. We have no time to run any algorithms except in hardware. So we're talking about hardware speed up. And I think everybody can see the problem here is what I need here, I can't decide on until here. That means there's a clock cycle lost. If I need something here in the next clock cycle and I can decide it here right now, I don't lose anything. So the decision point of jumping is here, and we proposed an alternative to move the decision point here. Now for branching, we're going to see life is a lot worse. Look at this. The decision point for branching is here, but we need to have it here, so we're going to lose 1, 2, 3 cycles in branching. And that's where we're headed now. Okay. Branch instructions cause control hazards. In the memory stage is when we make the decision about the branch, but I've already fetched the wrong instruction. We needed to know it right here. It's too late. So look at what happens. We have a branch, but we already fetched the LW. That's wrong. We already fetched this one. That's wrong. Tell me when we could actually make a good fetch. Would this be a good fetch? Nope, still backwards in time. Would this be a good fetch? Nope, still backwards in time. Sorry, but our first good fetch will be right here. Okay, so we're going to lose 1, 2, 3 instructions if we don't do something about the branch. So look what would happen. Flush, flush, flush. There's a good one. That's the right instruction. We branched to the correct address. That means that was wrong, that was wrong, that was wrong. Or we don't know, so let's just... Fixing the branch hazard by waiting means 3 flushes. That's a really negative impact on our CPI. Now branch instructions have CPI of 4. Yeah. And do you see why? It's because the decision point was here. Why did jump instructions have CPI of 2? Because the decision point was here. How could you get a CPI of 1? Make the decision here. Okay. Because it's fetching the next instruction. You have to know here so that this can be correct. If you know here, it's too late for this. Okay. So you see our problem here. And with branching, it's much worse. Well, we have to do something about this. That's just terrible because branches occur 15, 18% of the time. So we're not going to live with a CPI of 4 18% of the time. That's too much penalty. So one way to fix the branch control hazard, another way, a better way, I mean waiting is flushing out and waiting is one way, is to move the branch decision back earlier. We're making the decision here. What if we could move it to here? Then we'd only have 2 flushes. What if we could make it here? We'd only have 1 flush. What if we could make it here? No flushes. CPI of 1 if we make the decision here. CPI of 2 if we make it here. CPI of 3 if we make it here. Right now we have CPI of 4. So we want to move the decision point back. If I can make the decision here, then that's a good fetch. That's still a bad fetch. I have to kill 1 instruction. So if I'm able to move the decision point into the decode stage, then I could, with 1 loss of instruction, make a proper decision about my branch and fetch the correct one here. So BEQ, whatever happens here, you flushed it out. Now we know the target and we're good to go here. Okay? All right. So far. You okay with that? So, but that's if we can move the thing back. Now to reduce the delay of branches, we're going to have to change the hardware. If we moved the branch decision from the memory stage to the execute stage, then that would reduce the number of stall cycles to 2 instead of 3. But that would mean that we'd have to do in the execute stage what we're currently doing right now in the branch stage. So let's find out what we're doing. Okay? In the memory stage. In the memory stage right now, what we're doing is taking this value that we've got from the ALU, and don't forget that's one of our slower units, and we are saying, well, I need to AND it with, is it a branch instruction? And 0. And then I need to get through, I need to control this mux and get through 2 muxes and get to the value of the PC. So that means that that's delay. If I try to get the value of 0 and go through the gate and the 2 muxes and have it all here, that means that it's part of the delay of the execute stage now and not part of the delay of the memory stage. Does everybody see that when you start from here, it's really not a problem to get through here in time. But when you start from here and compute all this and then run the gate into here and then go through the muxes, that could be challenging. That's going to add to the delay path of the execute stage. Algebra, will you stretch the clock? Because don't forget, this has to fit in one clock cycle. If you pack too much in here, all you did was, well, slow down the clock so that it can be rahat and make it. So that would be a terrible cost, wouldn't it? Slow down the clock for every instruction just so that we reduce one cycle of stall delay on branches. Not a good trade-off. So what the slide says is, by moving that 3-to-1 mux, I'm calling it a 3-to-1 mux because nobody, when they're under time pressure, would say, oh yeah, that's a real good decision for speed. That's a terrible decision for speed. Right? I'm going to merge them together and make a 3-to-1 mux. It's going to have much faster through from in to out. So that would be my choice. It would be a 3-to-1 mux. So I'm going to have to add the AND gate and the 3-to-1 mux's delay to the timing path of the execute stage. And if I did that, I could reduce the flush number by 1. Now, I could also try to get it into the decode stage, and that would reduce it by 1 again. So now I would add hardware to compute the branch target address and evaluate the branch decision. So it's both. Do I branch? And if so, where do I go? Both of those now into the decode stage. That would be even better. Right? But it's going to require more things. Look, this required only this. Actually, only this. And here was our benefit. Now, this is going to require more. It reduces the number of stall cycles to just 1, same as that we had for jumps. But now we're going to have to add forwarding hardware into the decode stage. Forwarding hardware. You'll see it in just a minute. So computing the branch target address can now be done in parallel with the register file read for all instructions. It's only used, of course, when it's needed, which is branch instructions. So we read the register file all the time, and we compute if the two registers read are equal or not all the time, just in case it's a branch instruction. Right? And so to do that, we're going to need a comparator, new hardware, and we're going to have the AND gate and the 3-to-1 mux's delay now fitting in the decode cycles delay chain and all get done in one clock cycle. I'm not adding the AND gate, I'm just moving it from where it was to a much earlier point. And the 3-to-1 mux is now part of that, which has to be done in one clock cycle, instead of part of that, which has to be done in one clock cycle. Got it? It's the decode's cycle time now that can't be too much, including the delay through the mux on the AND gate. So now the question is, okay, we could do that, but what about this? You know, if you can get it from 3 to 2, if you can get it from 2 to 1, why not go for the gold here? Why not try to get it in the fetch stage and get a CPI of 1? All right, how would we do branching in the fetch stage? How would we, when we are fetching the instruction from the instruction memory based on knowing a certain address of an instruction, can you talk to me about a way to know what the next value of PC is? We already showed that if you know it's a jump instruction, you know what the next value of PC is. Now we're saying, if you know it's the address of a branch instruction, please tell me what the next instruction you should fetch is. You know, I could have a little table, a little lookup table. If my current PC value is this, meaning it's a BEQ or a BNE, please make the next PC value the thing coming out of the table. But how would I know what the thing to come out of the table is? Because branches go to different places, don't they? So I couldn't know for certain, because sometimes I might branch one way and sometimes I might branch the other way. But I could have a little bit, what could I do? Store them both, but then which one, when I say, okay, I'm at the address of the BEQ, you know, T0, T1 instruction, what do I want to pop out? The take it or the don't take it? Yeah, but the branch signal comes from a future time, you know, the value of the registers. No, I can't, in the decodes, in the fetch stage, I can't be depending on something from the future. That's backwards time dependence. In the fetch stage, all I know is the address of the instruction and anything that I might have stored in a table. Can you think of anything useful that I could store in the table that would help me to know which one to take? You know, who was right? I could store both addresses in the table. So if I say this is that particular branch, and that's my index, I got two possibilities that could come out. One is the go there, and the other one is the go there, pre-computed, right? So they're all ready to go. So I could know the next PC's value if I could correctly choose between the two, right? One is the pre-computed address of the branch target, the other is the pre-computed address of PC plus 4. They're both right there. Do I take this one and make it come out, or I take this one and make it come out? How do I choose if I don't know the value of the registers? Can I guess?
What if we both execute, we both go to two addresses and flash the wrong one?
Well, to go to two addresses means I need to have two instruction memories, and I fetch two instructions at the same time.
No, not at the same time.
No? Oh.
In sequence, but if it is the wrong one we decide, we just flash it.
Yeah, but then I'm back to this, and this I can do all the time anyway. So that doesn't gain me anything. Look, the last time I came and took the branch, I came to that same address, and I chose one of those two. Does that have any usefulness to me this time? Does the past history of a branch reflect any information that could be useful to me about my current decision? If it's a loop, it certainly does. Loops are taken anywhere from 90 to 99 to 99.99% of the time, and once they're not taken, right? Or the other way around. In other words, on a loop, you always make the same decision except once, and that once is when you leave, isn't it? Yeah. So lots and lots of branches are from loops. So I could have a very high prediction rate if I stored data about what I did in the past. Yeah. Tell me, do you store any data about the past here to help you make decisions about what to do today, tomorrow, and the next day? Yeah, God help you if you lost your memory. You wouldn't know your mom or your dad or your sisters, or you wouldn't know CS-224. You wouldn't even know what room to come to on Tuesdays and Fridays. I mean, we make all kinds of decisions based on past history, don't we? We store a record of important things and then use that to make decisions. I'm speaking very simply here, but this is the basis of computing, is decisions based upon stored history, right? Isn't it? So why not do it in the instruction fetch stage to help me have a high probability of going to the correct address with no stall? We're going to get to that in just a minute. All right, I'm jumping ahead, but I just want to make you think about, if this is better than this, why not go all the way to here? Why stop here? Aren't we greedy? Aren't we Ursula to make the machine go fast? Nah, I don't care, Hoja. Slow computers are fine with me, Dian Varma. I don't think so. I don't think so. You know, there's this inside the computer designers to push to make it go as absolutely fast as possible. So if you got a chance to make CPI lower, go for it. You got a chance to make clock cycle faster, go for it. You got a chance to make less instructions that have to execute, go for it. Right? Optimizing compilers and better pipelines and higher speed clocks, all these are, of course, very, very useful. All right, let's go on. All right, so we would like to even do this. What I'm going to show you is how to do this, and then we'll talk a little bit about this. All right, now for deeper pipelines, deeper than the MIPS, which is only 5-stage, the branch decision points can be even later, causing even more stall cycles. Think about it. The depth of the pipeline and the difference between the fetch and the place you make the branch decision is how many penalty cycles you have to make. And we've been working on doing this. But what if your pipe was so long that you couldn't get it? Oh, so pipeline architectures themselves will limit how much improvement you can make here in the stall cycles. Complex and long pipes have problems with hazards. Beta hazards, control hazards. They just can't fix them as well. Short pipes and simple pipes like this one do better. All right, now here's the thing that we're going to look at. Here's the branch instruction, and it's testing a register value which was changed here 3 instructions earlier. Now it's testing a register value that was changed here 2 instructions earlier. Now it's testing a register value that was changed here 1 instruction earlier. Got it? So we're going to look at all 3 cases and say, how can I manage that? What am I going to do? Did everybody see that? I don't want to test here the old value of register 1. I want to test that value of register 1 so I make the correct branch decision. Right? Everybody see that? Same thing here. I'm not interested in the value of R1 here. I want that value of R1 to be the one I use in my test. Okay, so this is in the write back stage, and now it's in the memory stage. And in the next one, it's in the execute stage, just one stage ahead of you, which you're in the decode stage. All right? Remember, we've said we're going to put our comparator in the decode stage. We didn't show that yet. Let me jump to that picture. What I need to do here, in the decode stage, is have a comparator. And you can see that what it's going to do is it's going to take the value from the register file RS bus and the value from the register file RT bus and compare them all the time. And it's going to tell me, are they equal, yes or no, which means take the branch, yes or no, right? Got it? Or this control is going to tell me if it's a branch instruction. Technically, that's the branch. This is, are they equal? You know, and just like our 0 coming out of over here, that's the exact same thing. It says they are equal. It's a comparator. It just does 32 bits, 32 bits. It says, are they all the same, yes or no? So this bit here is the same as the 0 bit coming out of here. Now, you'll notice there's some muxes here, and we're bringing something else into it. What are we bringing into it? This thing, which is, we're forwarding from the output of the ALU to here. Can anybody tell me why we would take something from here instead of taking it from here? Because it hasn't been written into here yet, and we're grabbing it from the place where it's been calculated. Understand? Look here. I've done an addition, and I've created the value of register 1. It's a new value. Or I've done an addition, and I've created the value of register 1. It's a new value. I don't want to wait till that gets all the way written back. I know it exists at the output of the ALU. Grab it and use it there. It's forwarding, just like we did data forwarding. That's why, just like the ALU inputs needed forwarding muxes, so do the comparator inputs need forwarding muxes. You understand? Yeah, and that means we have to now come up with control signals for those muxes to know when to do that and when to do that. Yeah. Notice this forwarded value can go to either one of them. So in one case, I'll take it and not take it in the other case, or vice versa, or I'll take it in neither case. But I won't take it in both cases, otherwise they would always be equal. Okay, you with me? So we're using forwarding muxes here. It's the same as we did here. When you need the data and it's not already here, you grab it from somewhere in the pipeline before it's written back and use it anyway. So here we go. In this case, when it's on the output of memory, the memory write-back register, forwarding is taken care of anyway by the normal register file write before read. In other words, it's going to get written before we read it out, so don't need to do forwarding there. In this case, when we need to forward it from the output of the ALU in the XMEM pipeline, we're going to need extra forwarding hardware. And I showed it to you. And it's going to have some code to control its multiplexers. This is literally the software which will be the algorithm or the logic in the forwarding control to decide what the multiplexer value is. This says the multiplexer value is high if we meet this condition. This says the other multiplexer value is high when we're in this condition. Low means take the standard values from the register file, but a high means take the forwarded value from the execute memory pipeline register. All right, are you with me? Did I lose you? You understand what we're saying? All right, let's check the conditions. It says if it's a branch instruction, and the branch field in the ID control says we're branching, and if the destination register isn't register 0, and if the destination register happens to be the source register in IFID, okay, there we go. The thing that you want to compare in the branch is the thing that you're about to write into in an instruction further up the pipe, then forward it please to me. I need it now for my comparison here. Okay? And this is for the other comparator. Same thing except instead of RS, it's RT. Yeah, questions?
What do we do while comparing, checking whether register RB of XMAN is 0 or not?
I'll be honest with you. You see this in every one of these. Okay, and I think what it's saying is if the destination register is 0, there's no need to do any forwarding because you can't write into it anyway. So therefore, don't waste your time. I think that's the meaning of that. But I don't think taking it out, at least I've thought about this, and I don't see what damage taking it out would do. It'd make the code simpler. I I don't really understand why, but in every single example, it has that test in it. Make sure that the destination register isn't 0 before we go ahead and choose our forwarding. So I'm sorry, it's not a good answer to satisfy you, but I don't see it's real important, to be honest. You know, and that's probably why you asked the question also. Yeah.
I don't understand. How do we decide what to compare before fetching the instruction? If we fetch and decode the instruction, it's already too late.
Okay. What we're trying to do here is make our branch decision in this clock cycle.
But we know what to compare in the branch instruction.
Yeah, but the problem is we've been comparing it way over here. And now we had to...
We need to compare it in the branch.
Yeah, there's 2 register values that have to be compared.
But how do we know what is in the branch, what registers in the branch instruction?
If you remember. Okay. BEQ, T0, T1, I don't know, target. Okay. Okay, can you, this is the I-type format. Can you tell me what goes here, 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 and here?
Yes, but...
Please tell me what goes here? Code for that. What goes here? Yep, the code for that. Tell me what goes here. Code for that. Tell me what goes here. Okay, great. So this is what we call the RS, and this is what we call the RT field. Okay. So this is the 32-bit instruction, right? So here it is. I fetched it. There's the 32-bit instruction. It's the branch instruction. Can you tell me what's going to go here and here? No. The RS, which is going to have the, whatever it is, 16 or 17 for T0, and RT. So if I put those 5-bit values here and here, a little while later, what am I going to have here and here? The value inside T0 and the value inside T1. That's correct. Now, I don't have to wait to here to subtract them. I can send them straight into a comparator right now and tell you if they're equal or not with 2 gate levels of delay. So all I'm doing is I'm saying instead of comparing here, let's compare here. Your question is, how do I know I got the right things here? It doesn't matter about that. If I have the wrong things here, they're also going to be the wrong things here. I have to get them, and their addresses are given here. If I put their addresses here, their values will come here. Their values will come there. That's how I know.
We assume that the way back here, there's an instruction, and we will do forwarding.
I'm not assuming. It's a branch instruction. There's no assumptions.
How do you know that T0 and T1 didn't change till we count branch?
That's what we're working on. Look. There's my T0. It's changing in the instruction just before it. There's my T0. It's changing in the instruction 2 instructions before it. There's my T0. It's changing in the instruction 3 instructions before it. That's exactly the question that we're trying to solve right now.
But how the machine decide that there's no instruction changing T1 till the branch?
Let's change the question. How does the machine decide if there is an instruction changing? Okay? All right? What we're saying, I'll just summarize what I've shown in the last 3 slides, is what we're saying is if it changes here, we don't care because we write before we read in the register file. The register file has the property that writes happen in the first half cycle and reads happen in the second half cycle. So I can write it here and it'll be in before I read it out of here in the same clock cycle. Do you know that fact? Write before read in the register file. This says write it back. This says read it out. But it's not going to have a conflict. There's no data conflict. That's why this is green. It's okay to write before read. We talked about that. We talked about changing the timing of the register file so that writes happen early and reads happen late in the same cycle. We divided it into half cycles by changing the timing edge. Did you remember that? We did that earlier. Okay, fine. So that's not a problem. If it's before here, it's already in the register file, and I don't care. But if it's in this instruction, or there, or there. Now notice, I don't care about any R1s here because those are reading them. I don't care about that. I'm only talking about changing them. This changes it, this changes it, this changes it. So there's only 3 cases to consider. This changes it, but it's too far back. It's already written into the register file. I'm not worried about any of these source operands, only about destinations. Do you understand that too? So the problem becomes, I'm not interested in an R1 here, R1 here. Benign and Hermes. I don't care about any because they're source and I'm reading. They're not changing. What I do care about is this column here. Did I change it here? No problem. It's already written back in the register file. I can read it out here, no problem. Did I change it here? Ooh, then exactly at the time when I need it, I'm putting it in, but luckily we changed the timing of our register file. Early write, late read. No problem. We solved it. Okay? Now I'm worried about this situation. Let's bring it a little closer. Now I'm writing it in the memory stage, and I got to read it out in the decode. That means it's not in the register file. Where is it? Where is it? Yeah, it's in one of the pipeline registers, partially computed. So that means we got to get it. We've got to take it from here and bring it around to here because I can't get it out of here. All right? Yeah, that's why I have forwarding. That's why I put these muxes in, to get the right value of T1 or T0, whatever, in order to bring it here so that I can have it when I need it. Okay, good. Now, let's go one more. What happens if it's here? What happens if it's exactly right there? And the answer is if the instruction immediately before the branch is making changes in one of the branch source operands, you have to stall. Forwarding cannot fix the problem. Okay? So that's exactly the answer to your question, but it's not a simple answer. It's a set of conditions and possibilities that we have to look at little by little and analyze each one to decide what we can do. So we said we can forward, and that'll help in the case when it's here. When it's here or before, we don't have a problem. When it's here, no fix. Does that remind anybody of anything? Change it here, use it here, one instruction later with no fix. What was that called before? Load use hazard with data, and we couldn't do it. This is with data, but we're not trying to calculate with it here, but in a way we are. We're comparing it, so you might say, yeah, we're going to change PC, not this, but we need it too soon. And forwarding isn't going to fix it for us. Now, can anybody see why forwarding can't fix it for us? Let's look at the hardware. I need a value here. When is that value available? The problem is the value is being calculated here. When is it ready? When is it ready? Clock Gelir Gelmez. Well, how am I going to use it here if clock Gelir Gelmez? Too late. See, this is a slow stage, and the output of the ALU is coming anjak in time to be latched into this register. So there's no extra time. So therefore, we don't have any spare time to say, oh, just draw a nice little line over here, bring it over here and use it. Imkan says we don't have any time for that. Okay? All right. Good question, Ur. Good question. All right. Did everybody see the issues here with trying to speed up the control hazards? Now, you're going to be doing the same stuff on your project. When you pipeline your processor, you're going to need to think about data hazards, structural hazards, control hazards, and how to fix them all. Okay? So we're modifying the pipeline pretty seriously. Look at this, and remember back in the first pipeline I showed you, and look what's new. This is new. Both of these are new. This is new. Both of these are new. This is new. This is new. This is new. We got all kinds of stuff on here that we didn't have when we first started. But of course, when we first started, we had a very soft pipeline which had all kinds of hazards and computed wrong data, and the only fixing was stalling. And stalling is doing things like this which lose efficiency. If you just do that everywhere and put zeros in, okay, you can do that pretty cheaply, but the better answer is put in some of this, 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 and then figure out when you need to use it correctly. Like this. This kind of code figures out when to forward. So in summary, this code helps me solve this problem. It tells me when to forward. If I have this situation, bring it in here by forwarding, make that one or that one. If I have this situation, this is the test to see, do I have that situation? Okay? Now, all of you are going to need to go and study this stuff. I do not believe that by looking at it for 2 minutes on the board, you're going to be able to have a deep understanding of it. It's in the textbook. And most of you, if you're still here, are probably going to be the project leaders on your team. I mean the technical leaders. You know what you're doing. You're still here. You're not kopmush from the course. So when we assign the groups after spring break, your group is going to be looking at you, Abi and Abla, and saying, I don't know, I'm really lost. Do you understand anything? And I hope you're going to be able to say, yeah, don't worry. I've been studying this pipeline stuff. I've been studying hazards and forwarding. I can manage it. Just help me, you know. Don't say, yeah, I don't know what I'm doing either. Let's all go home. Let's take a 0 on project 2. I mean, you have a week to learn it during spring break, and this is challenging stuff. As soon as spring break's over, it's going to come out, maybe before even. So you can watch the web and see if project 2 comes up even during spring break. The groups will be assigned, and you'll be off and running. There'll be a contact report, and 1 day later you have to find your friends and get going. And it's going to be just like the last one. Boy, the race is going to be on. We got about 4 or 5 weeks to get the second project in, so you can imagine, you know, the tempo is going to move right along. All right, I think I'm going to stop here. This is a good place to stop. Let's have a nice break the rest of the afternoon. I've got an exam tonight at 5:30. We've got all have an exam tomorrow night at 5:30. So I'll see you, and it's in this building. Am I right? Yeah, it's in this building, in these rooms here. Okay, great. Have a nice afternoon.